should be the last section. Ding, 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 ding. 6.5. Yeah. What we were trying to do is something like this. Okay, it's non-homogeneous. Now, something like this. Let's take a simple example. And what we have is, we eventually have to do the Laplace transform. And then we end up with something like this. Okay. After that, we will say, hey, we were trying to find the inverse function, inverse Laplace transform of this whole thing here. While I already know the inverse transform of the first one is going to be sine 2t. I just don't know what the second one is. Okay. And if we are lucky, this ft is going to be one of the special cases. For example, ft can be sine, cosine. We can have, for example, we can have constant, which we can handle. We can have exponential, which we can handle. Cosine, sine, we can handle. And the UAT, which is Heaviside function, we can handle. And finally, delta function we can handle. So far, we can only handle this 1, 2, 3, 4, 5, 6. Roughly 5 different type of force. But in real life, there can be hundreds of different type of force, hundreds of different type of external signals. So we want to say, well, how do we handle this case for a general ft? Maybe ft is going to be tangent. Maybe it can be square root, whatever. Okay, and we don't have the energy to find all the possible Laplace transform of them, because even if you find the Laplace transform of them and you multiply them, maybe you cannot find the inverse Laplace transform of them. Okay, so that's the key. Then the question becomes, if you know 2 Laplace transform and they were multiplied together, and you know the inverse of this, which is going to be, in this case, sine omega t, but in general, ft, and you know the inverse of this, how can you combine them together before you do the Laplace transform? So that's what we're trying to look for. And as we mentioned, they should be multiplied together in a certain kind of multiplication, which is called convolution. Okay, in another word, before you do the Laplace transform, if you convolute them together, then you should receive the Laplace transform of each separately and multiply together. Or in another word, if you know Fs and Gs, you should really convolute what you had before together. Okay, now we just need to define how to do this Laplace not Laplace, this convolution operation. But this is what we're looking for. Okay, that means once we know that, we have 2 things multiplied together. We know this one goes to sine 2t if you do the inverse. I know this one goes to ft if you do the inverse, because this one is LFT, right? Then I know how can I put them together. I just convolute these 2 together. Once we know the definition of convolution, because these 2 are multiplied together. Okay, so we were halfway done. We were trying to do the proof, and somehow I saw a gap in my notes. That's where we stopped. L F times L G equals 0 to infinity ft dt plus times gt e to the negative su du. We use u and t for different variables. S has to be the same though. After that, what we did was we combined these 2. We have ft times gt, gu, okay, times e to the negative s plus u, st plus u, d u dt. Let's do dt du. Okay. After that, we say we were hoping this one is going to be a Laplace transform of one function, which means we're expecting this one looks like e to the negative st dt. For that purpose, we should do a change of variable. We let t plus u equals tau. Therefore, t equals t equals tau minus u. And once you change that, this becomes 0 to infinity. T go from 0 to infinity, so tau go from u to infinity. Tau minus u gu e to the negative s tau d tau du. Okay, last time we stopped here, and that's where the gap is. Now we can do a simple transformation, and we can actually change everything to be doable. So okay, think about what you're trying to do. Basically, the region you're trying to integrate is you pick different u, and then once you fix u, you start from u to infinity to do your tau. So this will be the region of integration. For this particular integral here. Okay, from calculus 3. And then from calculus 3, we do know the fact. For this one, if you do it first horizontally, then vertically, or you can do it first vertically, then horizontally, it should not change the value. So we can change the whole thing by switching the order of these two. Okay, so instead of doing this, I should change this to f tau minus u gu e to the negative s tau du d tau. And I let my tau go from 0 to infinity. Then for each fixed tau, I should really go from 0 to this for u. This is u equals tau. Okay, that's where the gap was last time. But for the same region, we just changed the order of how we do the integral. We have this. Okay. With that in mind, finally we have this. That is okay. U e to the negative s tau du, and then we switch the order. Okay. Now take a look. What's inside here is a function of u. Let's call it hu. From here, you can see this is nothing but from 0 to infinity, hu, okay, e to the negative s tau d tau, which is the Laplace transform of hu. Then we finished what we need to do. Okay. And this thing in the parentheses is going to be the f circle g, f convolute with g. Okay. So define f convolute with g equal. Let's change tau to t because we're more familiar with t, but really it's just change of name. We call this the convolution of f and t. Okay, and according to our computation, L, f convoluted with g equals LF times LG. Or equivalently, if you know the Laplace transform of f and g. Okay. Then the inverse Laplace transform of this is going to be just this. According to our computation. Okay, we did some computations, which is not important. You should go over it by yourself for once to make sure you understand it. But the key takeaway is this, I would say the first time you see it, it's weird. This weird form is a way to put f and g together. Okay, somehow that thing is called convolution. And this one has a wide application in signal processing, image processing, and all kinds of things. Has everybody seen this before? Heard about it before? Convolution? We better explain it then. Remind me when I finish. We should explain what this means. It looks weird at first when you take a look. Okay, but that formula somehow should make sense. Well, it's weird, but it looks nice. It's symmetric. All right. Now let's go back to the example. This time we'll have a general ft, which we don't know what it is. Okay, you can put anything there. You have this one equals 0, y0 equals 0. You can still do the Laplace transform, which is super easy. So I will skip Ly equals L times LF. Before we stop here, because we do not know the Laplace transform of any function, we only know a few. Okay, but now the last step is y equals L inverse. This and that. Now you notice it's a multiplication. Then this one should equal, according to the formula we just did, convoluted with this. Now we know the first one. Shit, it's 1/2. Oh, why don't I just use 4? Either way, okay, 1/2. Convolute with the second one, which is, what's the L inverse LF? It just equals F itself. You do the L, then you do the L inverse. You don't actually have to know what the Laplace transform is. You do it, and then you do the inverse. You don't change a thing. Finally, write the formula. That is 0 to t 1/2 sine 2 t minus u fu du. That is the solution to this initial value problem for any f. All right. Is the idea clear? This does not look nice at all. Okay. So what we had before? Well, before, if you have one of the following, for example, if you have delta A, ft equals delta AT, you can plug it into this. That will be the solution. And moreover, you will be able to actually do the integral and find the antiderivative to simplify this one further. So eventually you receive a nice thing like this. Okay. So for certain choice of force, ft you put here, you will be able to do the integral. But in general, usually the integral is not doable. Then you have to keep your answer in this way. Okay. Nonetheless, it's a function of t. Once you finish the integration with respect to u, the only thing left changing is t. Okay. So this works only for special cases. The integral is doable. Then you receive whatever we have computed before, which looks nice. It's a single formula. But in general, the final thing looks like this. Sounds good? Okay. This will be the solution for harmonic oscillator with actually the external force put into your final formula. You put in a force, you got a nice solution. You put in another force, you got another nice solution. So this is actually the general solution for harmonic oscillators. Okay. In real life, how does people use this? Well, you need a formula for your yt, so you can make predictions, or so you know what the numbers are at different t. That's why you need this in real life. Okay. Now this one is given by this form. I don't care if it looks nice or it does not look nice. I just care about, can you produce the value of this function at a different t? Assuming you know f. Can you compute the yt? Because if yes, I don't care if your formula looks nice or not. Because whatever number I want, you can give me the signal at that time. Okay? And how do you do this in real life? You do the numerical integrations. Usually it's approximated by numerical integral. Okay. What do you mean by that? Let's go back to the basic of integrals. What is this? Okay. That's usually how we do an integral. We have integration by parts. We have all those kind of fancy techniques. Sounds good? However, this one only works for the easy cases. I can give you something which is not even hard. You can try everything you can. Integration by parts, U sub, trig sub substitution, whatever you know. you will find this one is impossible to do. Let's take a negative analytically. Okay, that means you cannot do it by hand. Meanwhile, does this one have an area? Of course, this one have an area. You can plot this thing. This thing roughly looks like this. So this thing doesn't have an area from 0 to 2. So if I ask you a question, what is this number? And the traditional antiderivative method fail. How can you give me the answer of this area which clearly exists? Is the question clear? Okay, how do you do this? You find the antiderivative, but in this time, the antiderivative is impossible. How can you do it? That's when you will use numerical integration. The easiest thing you can think about is basically Riemann sum. You take this one. You cut it into small pieces. Maybe 100 pieces. Then you take out your computer, you write a for loop, and just say, please sum all these 100 pieces together. That thing is not accurate, and the more pieces you have, the better the accuracy. Riemann sum is one way to do it. You also have other fancy ways to do it if you take numerical method. But nonetheless, can you see that this can be done by using the computer? Even though it will not give you the right answer, it gives you something very, very close. The more you do, the better the results. So this is called the numerical integral. Okay. That means if I have yt equals some random function, which I don't know how to take the integration, there is a 2. Even though I do not, for example, I put e to the 3u squared plus 2u, something like that, and I don't know how to take the integration, still okay? Can you see that for a fixed t, you can repeat this process to find the value? Maybe the value is 3.6 or something. Okay, and it can be more accurate if you do more. So that's how people did it. So even though this formula does not look as clean as what we did before, it's useful. It's very useful. All right. That's everything we need for convolution. Finally, like I promised, we can talk a little bit about the physical meaning of this. Okay. What's this? This one involves two functions. And if we are doing signal processing, let's just say f and g are two signals. We know a signal which is called ft. We know a signal which is called gt. Okay. The f convolute with g is nothing but a way for these two signals to interact with each other. And this is exactly the way. So, okay, so think about this as two signals, ft and the gt, interacting each other. Moreover, I will take ft to be an input signal. And the gt doesn't have to, but for this case, I want to take it to be a decay signal. And let me explain what it means. ft can be anything. You just come in. Dot. Let's take a discrete case, okay, for simplicity. This is the signal. At every moment, there's a new signal coming in. Sometimes it's 2, sometimes it's 5, sometimes it's 3. Signal just keep coming in. Sounds good? Second, every single signal, if I pick a t, is going to have some effect on this time t. Still okay? But to different level. And the principle is, whatever happens here has a stronger effect on this one. And whatever happened a long time ago will still have an effect, but a very small effect. Because the effect decay according to time. Does that make sense here? Okay, I shout to you. The people who are closer to me receive the signal faster, earlier. They have a bigger impact. They hear it more loudly. But if you're standing like 10 miles away from me, number one, it will take some time for my voice to pass to you. Second, when my voice reach you, my voice is way weaker than the original voice. Sounds good? Okay. Then I'm going to call this one a decay signal. It can be anything, but let's just make it easy. It's going to be this. So the further you are, the smaller the effect. This is what G tells you. Okay. Let's take this T to be 10, to be more precisely. And so I also need 10 points here. Something like that. Usually we can take an exponential decay, but we can have something else. Either way. This is your F, your signal. This is your G. Okay. Now here's the question. At time 10, how many signal have you received? You received a 10 signal. That is the signal at 0, 1, 2, 3, 4, 5, 6, all the way up to 9. Okay? Each one decay a little bit. The one happened at 0 decay the most. The one happens at 9 that do not decay. Still okay? Now the question is, what's the total? Let's just call signal. What's the total effect of the signal? Up to t equals 10. Sounds good? All right. So what's the total effect? That will be the effect of the first signal plus the effect of the second signal plus the effect of the ninth signal, all summed together. All right. Let's just do 11, F10 to make it clear. So I have 11 signals. Otherwise, I will mess up with the index. Okay. But it's not simply just a sum of these because this one just happened. It's pretty strong. This one has decayed for 1 second. Sounds good? F8 has been decayed for 2 seconds. F7 has been decayed for 3 seconds. And F0 has been decayed for 10 seconds. So before I sum them together, what should I do? I should adjust them by their decay. Good so far? So how do you adjust that? F0 has been decayed for 10. So I use F0 times G10. Remember, G10 is the smallest. F1 should be adjusted by G1, G9. F9 should be adjusted by G1, and F10 should be adjusted by G0, which means node adjust. It just happened. No decay. And finally, I summed them together. So let's see how we do it. We simply do I from 0 to 10. F, G, I, 10 minus I. The later the signal, the smaller the decay. The earlier the signal, the bigger the decay. Does it make sense? Okay, so it's almost this number multiply with this number. And then this number multiply with this number. So if I need to draw this multiply with that, this multiply with that, this number multiply with that. Okay, it's not exactly accurate. So can you see it's actually a one-to-one correspondence with F and G, but with G flipped? Okay, and to make sure that they sum together equals 10. So if you are 1 away from 10, which means you are 9, you should do G1. So this one start from 0, this one start from 10. Go in the middle, one step at a time. Things like that. I don't need to draw more. Okay, does that make sense to everybody? One signal is going to affect you. The other signal also goes like that. So if you try to imagine one of them is actually the decay, the other signal is a very simple principle. At time t, you accumulate all the signals before, but you cannot accumulate them all equally. Okay, think about it. For what happens at t, what you should really do is you should just integral 0 to t, g, u, du. That's the sum of all the signal up to now, right? But the earlier the signal, you should adjust it by a little bit weight. You cannot equally weight them. And the weight is given by this. So this is the signal. And this is actually the weight of the signal. At a different time, you should weight them differently. And that is how convolution is actually done. And now it should make sense. Two signals coming together. Okay. Questions so far? Now let's read the solution. We did this. The solution looks like this. Okay. What's this? That is the natural frequency. That means if you have something, you have a hammer to hit it, you will receive this. Okay. Then what do you do? At t equals 0, you hit it with F0. That's the external force, right? At t equals 0.1, you hit it with 0.1. You got another wave. still follow this pattern. At t equals a different time, you still have the whole thing. This one still follow this pattern. But can you see the whole sine wave is actually shifted to the right a little bit? Every time you hit it. Okay. So now if I draw a thing which is called t, I ask you, what's the sum of all the sine waves here? That's going to be the first sine wave plus the second sine wave plus the third sine wave plus all the possible sine waves. Sounds good? But for different sine wave, I should take a different time spot, because the later the sine wave happen, the earlier the effect should be in the original sine wave. Okay, or equivalently, if this is the original sine wave, for the first sine wave, I should take the effect here because you are this much from there, right? The second sine wave happened a little bit later. So technically I should just say, hey, take the same width, but I should take this part of the sine wave because it happened this much later. Okay. For that signal, I should take this part of the sine wave because it happened even later. Sounds good? So actually you are summing all these sine waves together. It's just like you don't have a sum anymore. You have an integration because this signal just happened continuously. So it's almost like externally you have this force constantly just hitting the spring. Okay, every time this one hit the spring, you have a sine wave responding with the same frequency. Still okay? Now just hit this thing for 100 times. Keep doing that. Okay, every time you just wait for another 0.1 second, you hit it again. Wait a 0.1 second, you hit it again. Then you say, what happens at time 10? That's going to be the sum of a lot of sine waves together. Each sine wave looks the same with the same frequency, right? But arriving at a different time. So that's what convolution really means. After that, if you read this one, this thing makes perfect sense. It's beautiful. Sounds good? You will see this thing later, okay? In other type of things. I can give you another example. You can think about this as, let's just do negative infinity to infinity. Okay. So what is this? Think about it. Whenever you put a heat source here, okay, the heat source decay, which means the further you are from the heat resource, the fewer heat you receive. Good so far? Okay, so if this is 40 degree, if you're very close to it, you probably feel 39. But if you are very far away from it, you probably feel 1 degree from this 40 degree because you are so far away from that. Okay, this is usually called a kernel. That's called a heat kernel. It quantifies how much effect is decaying according to how far you are away from the thing. Now, think about what's going on here. Let's fix a point. I want to know what the temperature here is. Let's just call it T. Good so far? And how many resources you have? You have a lot of resources. You have a heat resource here, you have a heat resource here, you have a heat resource here, and you have a heat resource at every single place, which is quantified by GU. Okay, at 0, you have a heat resource. At 1, you have a heat resource. At any time, you have a heat resource. Good so far? Some of them are hotter, some of them are colder. Now I'm asking, how much heat do I receive here? What do you do? This heat resource contribute this much because you are this much and you are that far away. Sounds good? This heat resource contribute this much. This heat resource contribute this much. So at the different location, you contribute for different decay. Again, now what you do, you just sum them all together. That will be the total thing you receive from the whole space. Sounds good? So that's again an application of the convolution notation. So from here you can see it's actually pretty natural. The further you are, the smaller the effect, right? And this is basically used to quantify how far away you are from T. And this quantifies how strong the signal there are. And then you combine them together. Okay, so yeah, let's just talk about distance from T. And then resource at T. Let's just call it source. Not T, U. Distance from T to U and source at U, you sum all these kind of things for different U's together. That's how you do the heat. Okay. One more complication you can think about, I won't talk too much about it, it's image processing if you have a kernel. Okay, think about it, you have a picture. Now what do? You start to have noise here. Okay, you give it some noise. Maybe it's a sharp light. Maybe it's something, your hands shake a little bit. Sounds good? Then the flaw here is going to affect the whole picture. But of course, the biggest effect is here. And as you move further, the smaller effects as you go. Sounds good? Okay, so actually this idea can be used for image processing too, for any kind of irregularities in your image. Once you do the convolution, you will be able to apply a filter, and after that, you will be able to know where the edges, where the points, where all the shapes are. All right. Okay. Any questions for convolution? I don't think the computation is that interesting, other than the concept is really important.